Hello everyone. So welcome back to our latest lecture session. So we were looking at a practical example, right, when the theoretical definition of an alkalinity is not valid. Yes, because we have, I think, we were looking at the case of an anaerobic diester where you have acetic acid being formed. Thus, your theoretical definition is not going to be valid because your acetate ion can either take the proton or the acetic acid can donate the proton, right. So we try to calculate by looking at H total 1 and H total 2 and the difference. We try to calculate H total and CO3 total, and we end up doing that. So now we need to look at the other aspects of the question. Let's look at what they are. So obviously the question here is about calculating the partial pressure of carbon dioxide that would be in equilibrium with this water. So in general, let's say your anaerobic diester, right, a very poor graph here. So you are going to have your particular solution here, and you are going to have some what do we say, headspace here. So you are going to obviously have a partial pressure of carbon dioxide, right. So the question asks us what is the partial pressure of carbon dioxide that would be in equilibrium with this particular solution now, right. We are not adding any other component. So that is something we should look into, yes. And also let us look at the other cases and see why we need to go through that, and say that assume that the diester begins to go sour. I mean, in general, let us say your acetic acid, right, is going to form methane or end up after the redox process you are going to have methane being formed. But if the kinetics is slower, let us say, what is going to happen, you are going to have additional or more formation of acetic acid. So that is what is happening here, I believe. Assume that the diester begins to go sour, as in production of acetic acid exceeds the removal of acetic acid to form methane. So the concentration of acetic acid increases, right. So here the rate at which methane is being formed from acetic acid looks like is slower than rate of production of your acetic acid. So the diester is beginning to go sour, right. So assume that this can be represented by the addition of 1500 milligram per liter of acetic acid. So additional amount of acetic acid present is equivalent to 1500 milligram per liter of acetic acid. If CO2 is not exchanged between liquid and gas, what will be the pH after digester goes sour? So assuming that it is a closed system, let us say, what would be the pH? So again, why do you need to calculate the pH now, right? In this particular anaerobic diester, you have different phases, right? Hydrolysis, acidogenesis, right? Acetogenesis and methanogenesis, right? And the relevant what do we say, microorganisms that are required for acetogenesis and methanogenesis, they are active only in a very narrow pH range, as in I think 6.5 to 8 or 7.5. Do not take my word for it, but anyway near the neutral pH now. So when you have excessive formation of acetic acid, that is taking place, what would you observe? You would observe that the pH falls down, right. So if the pH falls down, what is going to happen? Your whole what do we say, process is going to crash, because obviously the methanogenesis is not going to go through. You are not going to have formation of methane, which is what you are trying to produce, right. Gas that has high calorific value, right, which can be used for commercial purpose, let us say, yes. So that is one of the reasons why you would want to maintain a particular pH. So obviously you can either monitor the pH regularly, or obviously you can look at or calculate using Vimin-Tech or by hand, and predict what is going to be the pH and be ready with the relevant remedial actions, right. So again, let us look at part D2. So obviously now calculate the concentration of lime, right, which is a source of OH minus ions that would be needed to reach the pH 7 if no carbon dioxide exchanges. So in this case, we are just trying to calculate the partial pressure of CO2 that would be in equilibrium with the case as calculated in part A, right. And in part C, we are trying to predict what would be the pH, right, or drop in pH if you have a diester going sour, yes. And then because obviously you can't let the pH fall below, let us say 6.5, what are we trying to do? We are trying to add lime, a source of OH minus, the base, right, so that you bring up the pH again to what pH now? pH 7. Anyway, so now that we understood what it is that the questions are about, or what it is that we are trying to achieve, let us go through and see how do we go about this situation. So here obviously calculate the partial pressure of carbon dioxide that would be in equilibrium with this water. So that can be achieved just by plugging in the values from the last time. So I believe I should have stored them and not removed them from my particular case, but let me see if I remember how to do so. So earlier I believe we looked at pH was fixed at 7, right. And what else? We need to have acetate concentration. We had acetate at 8.33 if I am not wrong, right, 8.33, and the units though are millimole, right. Add that to the list, right. And what else is required though, right? We had pH 7, and I believe we also had to add alkalinity, and alkalinity was, what is it now? And I think we had in milli equivalents per liter, I think it was 34.7 or 34.734 I believe, okay, 34.734 in milli equivalents per liter. So, I am going to add that, and so we ran the Vimintek, right, and we calculated from this particular table CO3 total and H total, which we obviously do not need to do that because we already have that, but it is just asking, what is the question asking for? What would be the partial pressure of carbon dioxide that would be in equilibrium with this particular system now, right. So, as in it is not as if you are now opening up the system or such. If it were open, what partial pressure of carbon dioxide would maintain this particular pH and this particular CO3 total. So, you know, Vimintek has already what we say solution for that. It says, you know, if you just click on gases, it will give you an idea about the partial pressure that would be you know, in equilibrium with this particular solution, and that we have is 0.02 atmospheres, I guess, right. So, but one key aspect that to remember is, I guess this is a theoretical, I mean a practical question, but some of the values might have been off, because the carbon dioxide in an anaerobic diester, the partial pressure would be, you know, much greater than 0.2 atmospheres anyway, but anyway that is something for you from practical point of view. But the gas that would be present here in equilibrium with this solution would be what is it now, 0.2 or 0.02, pardon me, or 0.2 atmospheres, right. Anyway, so let us be done with that, and now move back to our particular case. So, I am going to restart Vimintek, right, so that I do not have issues further, because now I am not going to plug in alkalinity again. So, let us look at the question here. So, what is the first aspect? This aspect we are done, partial pressure of CO2, I think we calculated that particular value to be approximately equal to what now, 0.2 atmospheres by just looking at the shortcut tab that Vimintek has for us. And now we move on to estimating the pH if the diester begins to go sour, right. So, let us look at what we have here, and these are the values of H total and CO3 total from part A, right, part A. And this is what we, I believe we calculated from part A. And now let us say what is it, what is the new aspect that we have now? We have additional acetic acid HAC dot, and that at the concentration of 1500 milligram per liter, right. So, I want to convert this into millimolar units, and I think earlier we calculated the molecular weight of acetic acid as 60 grams per mole, right. So, dividing by 60, what is that going to be? 1500 by 60, and right, and so I think it should be around 25. Is it 25? 6 to 12, yes, it is 25, that is equal to 25 millimolar, right. So, what does this mean now? So, in effect the diester has gone sour to the extent that 25 millimolar of acetic acid or millimolar, pardon me, right, millimoles of acetic acid has been formed. So, now we need to take this into our account and be able to go further. So, how do we go further now? So, what factors are going to change now? Is CO3 total going to change? No, because do you have any components or, you know, of CO3 total here? No, CO3 total is not going to change, but what is going to change? Obviously your acetate total and H total are going to change, right. I should have also written down the acetate total here, but I think we know that that is 8.33 into 10 power minus 3. So, I am going to write that down here, right. So, by adding HAC at 15 or 25 millimolar per liter, how are these two particular total components going to change? So, that is going to be equal to acetate total initial plus this new addition of acetic acid, right, and that is going to be equal to what is it now, 8.33 plus 25, right, into 10 power minus 3, right, and what is that going to be equal to? Am I plugging that right? And that is going to be equal to 33.33, right, into 10 power minus 3, and H total is again going to be equal to H total initial plus HAC naught, right, and that is going to be equal to what do we have initially? It is 0.0482 plus 25 into 10 power minus 3. So, let us use Excel to maybe plug this in, right, and I think we already have this value. This is our particular case of H total, right. So, plus 0.025, right, and enter. So, we now have 0.0732, let us say, and where do we have that? That is equal to 0.0732, right. So, now we have our new conditions. What are they? We have CO3 total, that is still same as earlier, because addition of HAC will not affect CO3, you are not putting in any source of CO3. So, that is going to be equal to 0.0414, right. So, I have CO3 total, I have estate total, and I have H total. So, plugging this in, what can I calculate? I can calculate now the pH, right. So, again if you try to look at it holistically, you are adding in you're producing acetic acid, which is equivalent to adding more acetic acid to your initial solution. So, thus we included the effects of this addition of 25 millimolal acetic acid on our total components, right. You have case 1 and case 2 when you have more acetic acid. So, that is what we considered and calculated the total components of what is it, CO3, H total and estate total when we added acetic acid. Obviously, CO3 total is not going to change, obviously, because you are adding HAC, H total and AC total are going to increase, and that is what we calculated. So, we now need to calculate the pH, right. So, once you add this amount of acetic acid to the initial solution, what is the pH going to be? So, right, that is what we are going to plug in and look at it here, I guess, right. So, let us go back to VMinTech and hopefully we can come back to these numbers when we want to, and I think we need to calculate the pH. So, we are not going to look at that. I need to show the organic compounds because I am going to have estate total, right, and now I am going to have estate total, and what is that particular value, please? That is equal to 33.33, right, millimolal, and where is this particular case? Right, and then what next? I also have CO3 total, and where is that? And let us look at that particular value. Where is that value, please? CO3 total is 41.4, let us say, right, millimolal, and let us plug that in here. Right, and now I need to plug in H total, I believe, and where is that? H total was equal to 73.2 into 10 power minus 3 millimolal, right. I am going to add that to list, just check to make sure, look right, let us run it and see if we have made any errors, I guess. So, right, run VMinTech, and obviously now seems okay. And what do you see now? Obviously, if you added acetic acid at 25 millimolal to a particular solution, so we now see that the new pH has fallen down to 5.88, right. So, let us just plug this in here, and so now, so what is the new pH? It was, or it is now 5.89, right. So, that is something that we need to keep in mind. So, again once now the diester went sour, as in the rate at which acetic acid was being produced was greater than the rate at which the acetic acid was being reduced to methane, right. So, what is happening here? You have accumulation of acetic acid. So, thus you are ending up decreasing the pH, and we wanted to calculate the pH. So, now it is 5.89, which is considerably less than pH of 6.5, which is, I guess, in general the lower threshold for effective production of this methane, or for the methanogenesis, right. So, that is particular case. So, now you see that the pH is less than what you want. So, obviously, you need to maintain the pH. So, thus part D asks us what would be the amount of lime required to bring the pH back to your particular value of pH 7. So, that is what we are going to calculate, right. So, let us look at that, and let us just look at the question one last time. So, calculate the concentration of lime that would be needed to reach the pH 7 if no carbon dioxide exchanges, I mean considering that it is a closed system more or less, right. So, we need to go back to pH 7 from what is it now 5.9 pH, right. So, let us see how to go about that, and I believe we need to again write down some of our initial values, but we can come back to this slide if required, I guess, right. I believe we will need to look at some of these values or these values too. So, let us just highlight them here. Okay. So, how do I calculate this now? I can estimate lime dose, right. How can I estimate lime dose now? This is similar to your alkalinity, carbonate and non-carbonate. How did we estimate that? We estimate that by adding the amount of acid required to bring down pH from 7 to 4.5. So, here you are going to have a trial and error approach. So, we are going to we know the cases for the total components for pH of 5.9, right. So, we are now just going to plug in the same total components at pH of 7, which is the pH that we want to go to, and we are going to calculate the difference in H total, right. And from that we can calculate the equivalent amount of the lime required, that is from a trial and error. So, again what is it that we are trying to do? So, let us say we have pH of I think 5.9, right, and we have the relevant CO3 total and acetate total at this particular case, right, and you can calculate H total, right. And let us say if I am going to go to pH of 7.0 and maintaining the same CO3 total and acetate total, right, I am going to calculate a new H total, right. And what is this, or how can this particular pH increase to 7? Only when lime or a base is added. So, by calculating the difference here delta H total, right, I can estimate the amount of lime that is required, right. So, it is equivalent obviously because it is CaOH whole twice, CaOH whole twice, that is equal to Ca2 plus 2 times OH minus. So, it needs to be balanced by or normalized by a factor of 2, right. So, this particular lime dose is obviously then because it is 2 OH minus per lime, I mean per mole of lime. So, it is going to be equal to delta H total by 2. So, that is going to be equal to the approximate concentration of lime dose. Why do I say approximate? Because we have not yet covered the relevant aqueous complexes, I guess, right, but Ca2 plus will have can form complexes, but here we are more or less considering that Ca2 plus is non-reactive, right. So, we will then first estimate the amount of lime dose required, plug that in, and then see if that particular value reaches to pH 7. If not, we will have some trial and error procedure, right. So, again what are we trying to do? We will first plug in try to find H total 1 and H total 2 at different values of 5.9 and 7.0 and go through from that, right. So, let us go through from here please, and I need to go to Vmintek here, Vmintek, back to input menu. Did I specify any alkalinity? Okay, I specified alkalinity. To be on the safer side, I am going to restart Vmintek. Okay, now we are back to Vmintek, and let us look at our particular values here. What are our CO3 total and acetate total please? They are CO3 total is where is our case? CO3 total is new CO3 total is still 0.0414. So, I am going to write that down here. CO3 total is equal to 0.0414, right, and acetate total was equal to 33.33 into 10 power minus 3. Acetate total was equal to 33.33 into 10 power minus 3, right, and thus is at a pH of, what was the pH? We approximated at 5.9, right, at 5.9. So, because I am going with an approximation, I guess I can calculate H total, or I can also just use the pH H total from the previous case. What was the previous case H total? It was 0.0732. So, H total was 0.0732. This was the initial case, right. So, I am not going to run that. So, what is the case I am looking for? How much base is required to bring up the pH to 7.0, right. So, now I am going to plug in CO3 total. same case as above, acetate total, same case as above, and fix the pH at 7 and then calculate what is the H total, right. So, let us go back to Vmintech now and plug in CO3 total 0.0414 and acetate total, right. So, let us go back to Vmintech. So, the pH is now fixed at a particular value, right, and what is that? 7, okay, and I need to plug in acetate total and CO3 total, and first I am going to plug in acetate total. I think we mentioned that it was 41.4 millimolal, right, okay, and let us look at that 41.4, right, and okay, I just made a mistake here, 41.4 and it is millimolal. I am going to add that to the list. And what about CO3 2 minus, was it 33.33 millimolal or something else? Where is CO3 2 minus? Okay, it is right here. What is the, pardon me, CO3 total was, okay, I think I messed up the values. I think acetate total was 33.33 into 10 power minus 3, right, and CO3 total was 0.0414, is that right? So, I need to, I guess, plug that in. CO3 total was 0.0414, and what did I plug in? Okay, I plugged in the reverse. So, I think I need to just change that here. So, CO3 total is 0.04, acetate total is 33.33, right. So, I am going to plug that in here. And then CO3 total, and that I think is 41.4 millimolal, right, and let us just check that too, 41.4 millimolal, right, we are on the right track. So, I am going to add that to the list, 41.4 CO3 2 minus, acetate total is 33.33, back to main menu, pH 7 is fixed, and so I am going to run the Vmintech. And now I need to calculate H total, obviously, right. So, I am going to print to Excel, and here we have the relevant output, I believe. So, H total would be equal to, what are the components that I need to look at? H plus 2 times H2CO3 plus HAC plus HCO3 minus OH minus and enter. So, I get a value of 0.048, right, or 48.1 millimolal, let us say, right. So, let me plug that in here. So, now the H total was equal to, H total 2 was equal to 48.1 millimolar, right, and what was the H total earlier? It was 73.2 millimolar. So, let me just write that down here. H total 1 was equal to 73.2 millimolar and H total 2 was equal to 48.1 millimolar, right, and this was obviously at pH of 5.89, right, and this is obviously at a pH of 7. So, what causes this particular increase in pH 7, I mean pH, or the decrease in H total? Only when you add a base. So, the base that we are considering that we are adding here is lime, right. So, as we looked at earlier, we know CaOH twice is equal to Ca2 plus and times 2 times OH minus, right. So, the lime dose, approximate lime dose would be equal to delta H total by 2, right. So, 73.2 minus 48.1, let me plug that in, that is equal to 73.2 minus 48.1, enter. So, obviously, it needs to be half of this value, right, is equal to 25.1, pardon me, is equal to this by 2. So, I get a value of 12.55 millimolar, right. So, I am going to switch back here. So, lime dose is approximately equal to 12.55 millimolar, right. So, this is what we have. So, but first again this is the case when we assume that Ca2 plus is relatively non-reactive, which is generally valid, but the pH was still going to be slightly off when you consider this exact dose. So, we need to confirm whether or not when we plug in this value of 12.55 millimole lime dose, will we achieve our particular case. So, we need to just run the confirmatory run. So, let us run that here. So, the Ca total, calcium total is the new component, right. Ca total is equal to CaOH whole twice, right, naught, and that is obviously equal to 12.55 millimole. And what else? We need to also calculate H total, that is equal to H total initial minus 2 times CaOH whole twice, right. This is the amount of base we are adding, 2 times because 2OH minus, right. H total initial minus this, and that is something, let us calculate that. What was H total initial? That was 73.2, 73.2 minus 2 times 12.55 I think was 25.1, right. This into 10 power minus 3 molal. So, let us just plug this in, 73.2 minus 25.1, that is equal to 73.2 minus 25.1 and enter. So, 48.1. So, that is equal to 48.1. I guess it is more or less same of what we arrived at earlier, right. But let us just plug this in and in vmintek and see if we are going to get the relevant values or not. So, obviously, we need to plug in H total, Ca total, and what else, CO3 total and acetate total, right. And what are these values, CO3 total? So, CO3 total was 41.4 millimole, 41.4 millimole, and acetate total was 33.33 millimole, right, 33.33 millimole. So, let us plug this in into vmintek, back to input menu. So, I think CO3 total and acetate total should still be present here, acetate, right. So, we do not need to change that, we need to add Ca total, and where is that equal to? Okay, and the value of Ca total was supposed to be equal to 12.55 millimole, right. Okay, so this has to be 12.5. And the units are millimolar. I am going to add that to the list, and obviously I need to plug in H, right, and how much was the H total now? What is the H total here? Right, I need to look it up here. H total is equal to 46.1 millimole, right, 48.1 millimole, right, okay, 48 millimole, and I need to change that value here, 48.1 millimole, units are still millimole, right. So, obviously, the pH needs to be calculated, it is not fixed at a particular value. So, let us just view and edit the list. H total 48.1, acetate total 33.33, and the other values, back to the input or main menu, and I am going to run mintek, right. I see that the pH is 6.95, not exactly 7, right. So, I need to obviously increase the concentration of what now? I need to increase the concentration of lime slightly to be able to arrive at my particular pH of what is this now, 7. So, and why is this? If you look at that, the reason for this particular case is that Ca acetate, CaHCO3 and CaCO3, right, you have some particular complexes being formed, right. In the earlier case when we looked at this particular example of adding lime and calculating H total difference, we assumed that the Ca total, right, or Ca2 plus was relatively non-reactive, right, but that is not the case here. You have aqueous complexes going to be formed, and this is going to be our next session. So, until now we have discussed acids and bases, right. So, here as you see, the Ca2 plus is not relatively non-reactive, it has or it binds with the other ligands, right, which are acetic ion, acetate ion, HCO3 minus and CO3 2 minus, right. So, these are called aqueous complexes when you have a metal and a ligand, right, which is an electron rich species, metal is an electron deficient species, and then you have a more soluble complex, right, that is formed, that is going to be called the aqueous complex, which we are going to discuss further in the next set of classes. So, anyway, with this particular, so how do I go further? I just need to increase the lime dose to be able to arrive at my pH 7, that is a trial and error case, so that I can do that, but we are not going to do so. So, in the next set of classes we are going to obviously start looking at the next major aspect, which is acids and bases. So, at this stage, you know, it is just worthwhile to look at what we have been up to so far, right. So, until now what have we been up to? We looked at the basics, equilibrium, how far can the system go, right, or travel, and kinetics. This gives us an idea about how fast can this system go, right, how far can the system travel, how fast can the system go, let us say, right. So, after this particular aspect we moved on to the major aspect of acids and bases, right, which we discussed for I think 1/3 of the class until now, or more than half of it, which is a major aspect in our environmental engineering, right. And now we are going to move on to aqueous complexes, right, aqueous complexes, which would be of great practical application in most cases where you have any metals present, right, or you know when you have natural organic matter present. So, metals you would present in, let us say, in coagulation and flocculation, let us say, when you are choosing the type of coagulant use, let us say, right, or when you have contamination due to a particular metal in soil or groundwater, right. Again you have complexes being formed, and that is another aspect that you need to look at. Why is that? When you have complex being formed, in general the metal, or you know, the total metal concentration tends to increase. Why is that? Because aqueous complexes are generally more soluble, right. So, that will, you know, in general lead to a total concentration of your particular metal increasing. Anyway, we will go through this in the next set of classes. So, aqueous complexes, and then we are going to look at precipitation and dissolution, right, and the last aspect we are going to consider is redox. So, we are done with this and this. So, we are going to briefly talk about these two aspects, aqueous complexes and precipitation and dissolution, and move on to the next major topic, which is redox process, something that is the backbone of environmental engineering, I guess, right. So, again what is the common factor between, or how can I differentiate between these three aspects and redox reactions? Obviously, in acid bases, aqueous complexes and precipitation and dissolution, the oxidation number or oxidation state of your particular atom or your particular compound does not change, right. It is only the coordination number that changes, right. But in the redox process you have a change in the oxidation state of your particular compound or the atom, pardon me, right. Okay, with that I will end today's session, and we will move on to aqueous complexes from the next set of classes, and thank you.